Lesson 13, Newton's second law. So we're blitzing through the laws. We were able to explain Newton's second law. The goal of today, by the end of it, is you should be able to go, you should be able to name Newton's first and second law. I've got some extra slides at the end that I would like to be able to get through, but we're going to stop when we get to the end of Newton's second law because we're not going to go through Newton's third law. That's going to probably be the goal of next, and that's going to be probably the major goal for next Tuesday's class. And then what we'll do is we'll spend some time working on the next idea, which I think will be motion 5. So yeah, and then after motion 5, I think there's only one more motion. There's only one more worksheet. And yeah, these are the worksheets that I'm going to use eventually to make your report to see if you guys have been keeping up to date with the homework. And that's, yeah, a good question from you guys earlier, which is, do we need, like, how do we get help? Yeah, I don't mind if you don't get it all of it done, but if you're showing me you need help and you make an attempt to learn the stuff, then, you know, that's the main sort of thing. Let's talk about Lise Meitner. Now, she was an Austrian physicist that was one of the most accomplished females and was one of the main scientists helped uncover nuclear fission in the 1900s. Nuclear fission, for those of you that don't know, is when an atom breaks up into smaller atoms. Due to the invasions of Nazis in 1938, she was forced to flee to Stockholm, and there she was able to continue working with her closest collaborator and chemist Otto Hahn. Her involvement with the discovery was overlooked when Hahn was awarded the Nobel Prize in 1945 for their discovery. So her name was intentionally left off the report due to double standards that people in the society held back then, only because she was female. She wasn't seen worthy enough to receive any recognition for her work, and therefore her work was stolen from her. Lise Meitner is one of the sadder situations in physics. Is essentially, her work was pretty much completely ignored, and yeah, she actually did a lot of the hard work for figuring out nuclear fission, and because she was a woman, she was ignored. What I found out recently about Lise Meitner, which was another really shocking twist in this story, is that so she because she fled Austria because she was Jewish, and you know the Nazis were invading, and they didn't care if they didn't care who they were, but her research into nuclear fission led them to build the atomic bomb. So, and she did not, by the way, she was she was completely against the atomic, like using weapons of mass destruction. But it's kind of like, and a lot of people have like, you know, started to curse her because she was the Jewish woman that invented the atomic bomb that could have been used by the Nazis. And so people were like, and it's just like, it sounds like Lise Meitner was an absolute genius, and yet she got like ignored because she was a woman, and then when she did get paid, people did pay attention to her. They were like, "Oh my God, you invented the atomic bomb! You're a horrible person." It's like, well, no, she pretty much made it possible for clean energy for hundreds of countries, you know, going forward. So yeah, I don't know. I think she was definitely worth talking about. This was a made by Najila, so good job there. She did her justice. And she also did a great job here explaining why it was stolen, which I really appreciate. Let's go through the rest of this lesson now. Now, the last time I talked to you guys, we were talking about Newton's first law. Now, Newton's first law is all about an object in motion will stay in motion, an object at rest will stay at rest, unless acted upon by an unbalanced force. Now, that's going to be today's goal. What does an unbalanced force look like? What does it do? So we said that an object at rest will stay at rest, and it's got to do with inertia. So objects just don't really like to have their velocity change. They don't like to speed up. They don't like to slow down. They don't like to move at all if they're stationary. And that's this idea of inertia. The heavier an object is, the more inertia it is, the more likely it'll just keep its current velocity or speed So we looked at two major examples that we sort of dealt with these of inertia. The first was an object in motion will stay in motion. So the example for that was the train. You're stranding on a train, you're in motion. Even if the train stops, you're going to keep moving forwards. The opposite to this idea is the idea of pulling a tablecloth out from underneath a set of plates. The plates stay where they are, even though the tablecloth moves. So both of those are examples of Newton's first law. But the tricky part with Newton's first law, and the reason that it took them so long to figure it out, is because objects in motion don't stay in motion. They stop moving. But the only reason they stop moving is because there's an invisible force, the invisible force of friction. If we reduce friction by using polished surfaces or going to space, or sometimes you can do some experiments in the air, you reduce friction, you can see that objects will usually try to stay in motion for as long as possible. So yeah, that was the first tricks with what was Newton's first law. Newton's second law is sort of like an extension on this. To do with Newton's second law, I'm going to ask you guys my standard question for this, just to see if you guys can understand Newton's second law or already know it based on just general idea. This is a thought experiment. I'd like you to write down in chat your answer to this question. The question is, a spring is designed to provide the same amount of push to a ball, so the same amount of force. One ball is made out of plastic. The other ball is made out of steel. Which one will go further? I want you guys to write one sentence explaining it. I'd like you to put it in chat, or if you just want to write it down in your book, that's okay too. But I would love you guys to send me an answer. Which one will go further and why? Why do you think it is? It going to be? And by the way, both the plastic and the steel ball are both the plastic and the steel ball are the same size. I'm not going to move on until I've got at least 5 answers in the chat, and there are 16 of you. So yeah, I've got one answer. It's a private answer, but that's fine. I want a couple more. Which one's going to go further and why? I got 2 answers. 3. I've got 4. And I've got 5. Okay, cool. All right, let's now start talking about it. Thank you for your answers. And of all 5 answers, only Everest put his publicly so people could see it. But that's okay. 6. Erica has also done it. So we've got plastic. Looks like we've got 2 votes for plastic and 4 votes for steel. So now a lot of people saying the plastic one will have with the less mass is going to go further. People saying the steel ball, because it's a heavier mass, will go further. Ewan saying the plastic due to the fact is lighter. There is more, and he said meaning that there is more being applied to the plastic ball spring. Oliver saying the metal will go further, is less like there's friction acted upon it. That's an interesting approach. Steel, because the heavy ball will constantly keep the speed up, but soon slow it down. And then Dylan saying plastic, the lighter, so there'll be less resistance to wind pressure. And yeah, okay. So what is the correct answer here? I really like, by the way, Ricardo steel ball has more inertia. And that's a good point. A lot of you guys are getting some really good points here. It's actually showing me not only that you're actually making a good guess. So the answer is interesting because it takes into some of your ideas into account. And the answer is actually, for which one will go further? The answer actually is the plastic ball will go further. Now, a couple of people saying, the couple of people saying the heavy ball will go further, and I would challenge you guys to think about this in your own situation, right? I want you to think about this. You've got, like, imagine that you've got this really, really heavy. Imagine that you've got this really, really heavy medicine ball and you've got a soccer ball, and I'm gonna ask you to kick both of them as hard as you can. Well, you're going to be able to kick that light soccer ball quite far, but that heavy medicine ball is probably not going to go very far. It's kind of probably going to break your foot if you try and kick it. So the light plastic ball, and yeah, I use the word plastic because I wanted you guys to think, yeah, is going to go further. Now the question is why? Why does the plastic ball go further? Well, because
Wait, so didn't you say that they're both the same mass?
no, they're not both they're both the same size.
Oh,
If they're both the same mass, then actually it wouldn't actually make a difference. But they're both the same size. So now let's talk about one of the interesting ones. I'm actually going to say what Ricardo said. It's like, well, the steel ball has more inertia, and in that case, Ricardo was right. The steel ball does have more inertia, but the problem with the steel ball having more inertia means that it's going to be, you can think about this in terms of inertia, it's going to be less likely, less willing to change its, it's going to be less willing to speed up, to change its velocity, because it doesn't want to change its velocity. So it's going to be less willing to speed up. So that's why that's how inertia plays into it. But there are a couple. The main way that I wanted you guys to do this is just to think about why. Yeah, because it's lighter. So that gives us this idea already that we have this sort of thought. Okay, so if you apply a force to a light thing, it'll speed up really, really quickly, and it will probably go a lot further. Whereas if you apply a force to a heavy thing, probably won't speed up very much. So let's see if we can figure out, well, what's going on in this situation. How do we explain this using Newton's laws? The explanation for that is here, Newton's second law. So when an object does experience an unbalanced force, so let's just say your forces are no longer balanced, if it does experience an unbalanced force, it will accelerate proportional to its mass. Force equals mass times acceleration. The more massive it is, the lower the acceleration is. And that's exactly what's going on in our steel versus our plastic ball example. A steel ball has a high mass, so therefore its acceleration is going to be very, very low. It's not going to speed up, and so therefore it's not going to go as far. Whereas if you have a plastic ball which has a very low mass, it'll have a high acceleration. It'll go really, really far because it's able to accelerate, it's able to get to a high speed really quickly. So that's the difference between the steel and heavy ball, and that's what Newton's second law of motion is. There's only, this is the only real way to write it down. So I'm going to give you guys a chance to write this down, and then we'll keep moving on. We'll do some examples of Newton's second law. Newton's second law is a bit easier to do with examples. So I'll give you guys about 45 seconds to jot this down. So yeah, ultimately I feel like this law is probably the easiest law to understand. If you push something, it'll start moving. That's pretty much it. If you push something, it'll start moving. If you apply a force to something, it'll start accelerating. It'll start moving. No matter, And if you push something really, really hard, it'll start moving really, really quickly, which we know. If you tap a soccer ball, it'll roll a little bit. If you boot a soccer ball, it'll fly. But of course, the mass is also important. If you try and kick a soccer ball, that's really easy. If you try to kick a medicine ball, it's not going to, even with the same amount of force, it's definitely not going to go as fast. Definitely not going to have the same amount of acceleration. So what we're going to do is we're going to do two examples of this. We're going to do an easy one, and then we're going to do a bit more of an application one. The easy one might be something that you may have seen last term in year 10 science, but the second one is definitely something new. So let's give that a crack on this next slide. If I can change the slide. Yeah. So let's look at this first one here. A hammer has a mass of 1.5 kilograms. What acceleration is needed to ensure it hits a nail with 40 newtons of force? How do we do this question? We're actually going to do this question the same way we've been doing all those other kinematic types questions. What we're going to do first is we're going to jot down all of the relevant information. So first we've got a mass of 1.5 kilograms. M equals 1.5. Now, you want to try to always attach a symbol if you can to the term that you're using. So mass, same way that we were attaching symbols to velocity and acceleration and things, you want to do the same thing. So mass equals 1.5. The acceleration needed to ensure it hits a nail with 40 newtons. So F equals 40. What is the question asking for? Question's asking for A, because it says what acceleration. Now, if I put down our equation, F equals ma, well, again, we have a thing that we now need to ask the questions like, is this in the form, is the equation now in the form that will allow us to solve the problem? The answer is no. We want no acceleration. This is not an equation that will allow us to work out acceleration. This equation allows us to work out force. We need to divide both sides by A in order to get this to work properly. Some things popping up in chat. Ricardo, I haven't got time to do that at the moment. Sorry. I can do that at the end if you'd like. I'm just halfway through a question. I'm not going to go back. So we're going to divide both sides by A. No, sorry. By M. Sorry about that. We're going to divide both sides by M because that will move M away from this side of the equation. That gives us A equals F divided by M. Now we've got our force. Our force is 40 newtons. Our mass is 1.5. 40 divided by 1.5 is going to be about 26.7 meters per second squared. And I'm going to write down. I'm going to put a direction here just in case, because like it does say what is the acceleration. The acceleration needs to have a direction. So that's how I calculate. And it's a hammer, so I'm hitting it now, so I'm putting it down. So that'll do. As long as there's a direction, even if it's not always the right direction, it's as long as there's a direction, you're showing the teacher or the examiner that you understand it has to have a direction. That's how I can do that one. So this one's an interesting question. We've taken out the important facts, an equation, but to rearrange it, and then we've got an answer. I'm going to make a start on the next question in a second. I'm going to give you guys maybe 30 or 40 seconds to copy that second question down if you want, if you've already copied it down, you've got 30, 40 seconds to give it a try before I do it. So if you want to give that second one a try, knock yourselves out. But I'm going to go through it in about a minute or so, or maybe 30 seconds. Okay. Now that top one, that's designed to be similar to something you may have seen before. That should be maybe not the most complicated things. Someone's asked the question, do I record these lessons? And yeah, I do record these lessons, and I try to upload them to YouTube actually on a regular basis. I put the playlist on the Google Classroom, so you can watch at least lessons 1 to 8 I've uploaded so far. I haven't uploaded many since then. It takes me a while to sort of get them all ready. But yeah, I will be uploading this one eventually as well. So if you want to see a more thorough breakdown of all of these types of questions, you can go back there and re-watch this later on. But that's not an excuse not to come to the class, because obviously it takes a couple of lessons before I eventually, it takes me sometimes a week, sometimes longer before I eventually put them up there, because it is a very intensive process. It kills my internet pretty much. Let's do this question. How do I do this question? So let's read through it first. The 200-gram glass is pushed off a 1.2 meter high table and takes 0.5 seconds to hit the ground. What force will it hit the ground with? Okay. So we're looking for a force. That's the first thing that we're going to try and figure out. The end of our question. We've got what's can someone tell me, and we're actually going to open this up to some chat. Can you guys tell me what are some important maybe values that I can extract from this question? What are some important ideas that I can pull away from this? I've already got one. I've already got force. What's something else? 200 kilograms of mass. 200 grams of mass is the glass. Now, this one is the one that I catch a lot of students making mistakes. The mass is actually 0.2 kilograms. You've got to give your mass in kilograms. And if you don't, you won't be able to get the correct answer. So that's what you need to do, that conversion. I did that conversion on the fly. I did 200 divided by 1,000 in my head. But if you don't know how to do that, you can just go, 200 divided by 1,000 equals 0.2 kilograms. You can just do that if you want. What's another important idea? So if I was to do this question, right? Let's just say I was to do this question. I want to calculate F. F equals MA. I'm stuck. So I've got M, and I'm going to quickly read. I haven't got A anywhere. So what other information have I got? Can I find out A? Is there another formula I could use? There's 2 points. You has already figured out what A is, but how did you get there? What did you do to figure out what A was? You sent it to me privately. Just figured it out. Okay, so he went 1.2 times 2. So he took that 1.2 meters. The idea of how to solve this question, guys, is to say, well, I don't know what A is, but I've got 1.2. That's going to give me an X. X is 1.2. Yep, sure. It takes 0.5 seconds to hit the ground. Hey, this is starting to look X. I've got T. This is starting to look like a kinematics question. XT, the glass is probably not moving at the start, so we're going to say U equals 0. So I can now work out a formula that has, pardon me, XU, and I'm going to find out what A is. And if you figure out what formula that is, that's going to be this one, X equals UT plus half AT squared. Now, if I plug that in, that's not going to be useful though, because I want to calculate what A is. Now I know that U is 0, so that's going to cancel that out. So that's going to give me X equals half AT squared. If I rearrange this, I'm going to skip the rearranging because I don't think that you guys can do that. A equals 2x divided by t squared. A, which is going to be, is a 2 times 1.2 divided by t, which is 0.5 seconds. 0.5 squared. That's going to give me a value for A. 2 times 1.2 divided by 0.25. It's going to give me 9.6 meters per second squared. Now, if I've got a value for A now, I've got a value for M, I can calculate the force. F equals 0.2 times 9.6 equals 18.43. Now again, this is designed to get you guys another chance to, I'm not going to give you many types of questions like this. Usually I'm just going to give you mostly questions like the top. The bottom question here is just to sort of show you guys, you can now, and it's trying to show you guys the power of what you know. You guys now have these kinematic laws at your disposal. So you can mix them with other questions. You can add them to force questions to find out acceleration. And if I apply a force, you can use that force to find out an acceleration. So that's how you can go back. That's how you can use it to your advantage and why we would use it. This again, as I said, I'm probably only going to give you guys questions like this towards the end of worksheets and the end of tests, because it's designed to really test your knowledge. Can you take formulas from 2 different chapters and apply them together? We do this all the time in maths, where we take, oh, well, now that I've taught this idea, I can now, like this indices idea, I can use this in a later topic with indices in it and algebra. It's like, oh, now you guys know this algebra topic, I'm going to apply it here. So now you guys have the kinematic formulas. I can now use those kinematic formulas in Newton's second law examples. I'm going to bust through a little bit longer now. Are there any questions on what I've done for either of these 2 examples, the top one and the bottom one? If there's no questions, then I'm going to keep going for a little bit. Oh, hold on. The class ends at 12:36. Okay, I've got one more slide to go through, and then that's going to be it. So I'm not going to be able to go through the last one, but that's okay. So the last slide that I'm going to talk to you guys about before the class ends, it's going to be just this one here. Now, this is actually a topic that I've taught many times to year 7 students, and it's one that we sort of talked about a little bit, but yeah. And it actually doesn't come up again in year 11 and 12. In year 11 and 12 physics, what we usually just do is we just say, we're just going to ignore this word weight. But I think it's always important to just talk about it, especially because like it's a word that gets used so often in common language that, you know, we know what it means. What does it mean here? So the difference between weight and mass, and this applies to Newton's second law. Weight is actually a force. Weight is when we officially when I say officially in physics context, weight is a force. It has a direction, and the weight force is caused by the gravitational pull. Okay, so that means that you can weigh different amounts depending on what your gravitational pull is. If you're on the moon, you will have a different weight to if you're on the Earth. If you're on Mars, then you'll have a different weight than if you're on Pluto or wherever. It's also why people say, oh, I felt weightless. It's like when you feel weightless, you actually don't feel any force pulling you, pushing you around because of gravity. That's what weightlessness feels like, is that you don't experience the same force. You can actually feel weightless on Earth. If you have, if you apply a force upwards to counteract the gravity, or if you are falling like skydiving, you will feel weightless because you don't have the same push. You don't feel the same push. However, mass, which we've been talking about F equals ma, mass is not a vector. Mass is the measure of the amount of matter inside of an object. It doesn't change depending on gravity. You will have the same mass if you're on the moon, if you're on the earth, if you're on the surface of the sun, you'll have the same mass. But your weight, the force that you get pulled down towards the surface of whatever you're standing on, changes. Now, we'll quickly tell you guys that the formula that we use, I'm actually going to put this formula down the bottom, is actually called F equals mg, where g is the gravitational acceleration. And on Earth, the gravitational acceleration, g, equals 9.8. However, because you guys are in year 10, I'm going to make life a little bit easier for you guys. We're actually not going to use g equals 9.8. We're just going to assume g equals 10. We're just going to round it up. The reason for that is this is going to make a lot of our calculations a lot easier. And when we do need it, we're just going to assume g is 10. Now, saying that, and I always get a question like this. Someone always say, if I use 9.8 in the question, are you going to mark me as wrong? And the answer is no. If you use 9.8, I'm not going to mark you as wrong. I would prefer you use 10 just because it's easier and it'll be less stressful on you guys. If you want to do 9.8 though, because you want to be 100% accurate when you don't need to be, then sure, go right ahead. That doesn't bother me. Ladies and gents, I'm not going to go through these free body diagrams today. We'll do that next Tuesday. I'm going to wrap up the lesson here.